Hello friends, today I'll be doing topics on module theory. So we begin by first specifying what is the definition of a module. So first thing is definition. So to define a module we need two things. We need a ring R and a group M. So then if we have this, then we say M is a R module if M is a group under addition, and if you take an element R from R and if you multiply it with an element M from M, then this should stay inside M. Okay, this is the thing. Additionally, we'll assume that ring R is unital, as we always do, and that is unit element 1. Okay, and then there are some distributive and properties and associative properties. So for example, if there are two ring elements R as M, then this should be equals to Rm plus Sm. If I have R, a product of a ring, because it's a ring, so if it can be decomposed as this, then it is also equals to this. And then distributive from the module point of view, module elements point of view, so this should be Rm plus Rn. So this is the thing. So this is like a ring acting on a module. If you are familiar with group action, this is very similar. So this is a definition of a module. Now a related definition is of a submodule. So submodule N of a module M. So definition is exactly so. N should be a module in itself. Should be a module in itself. No, okay. So the non-trivial condition to check is the ring action is good enough. So that is to say, if R belongs to R and if I choose an element N belongs to N, then it should stay inside N and not stay in M, then we say N is a submodule. Okay, now let's look at some examples. So the most obvious example would be if you take M equals R. So this is to say कि R is a R module. So does this satisfy definition? R is definitely a group, and all these ring properties, all this hold trivially. So this is a module. Yes, module. In fact, I can go a step further and say, what about M equals to Rn, where Rn is the product which is equals to R cross R cross. This is the N times N ring product, where every operation is defined component wise ring operation. So addition of two elements in a ring, and if you multiply two elements, how they multiply in a component wise manner. Okay, so is this a module? So clearly M is a group because Rn is a group. Let's check this property. So R plus S into M, what is it? So M essentially would be M1 dot Mn, and if you multiply Okay, I have to specify what is a group action. So group action is just each element is applied to each component. So this would be r plus s into m equals to rs mi dot dot dot. So now this again belongs to Rn. Sorry, not this R, the ring R. So all this exercise, all this properties is very easy to verify holds true. So even this is a module. Yes, module. Now another example I would give you. Suppose M is a R module. It's given. And suppose there is an ideal I such that I into M equal to 0 for all I M. Okay, then I will claim Km is R by I module. So how is the group action defined, or how is the multiplication with this defined? So it's easy now, because any element of I, R by I can be written as R plus I. This is the equivalence of element. So if I multiply it with M, it will give me Rm plus Im. So as we know, this term goes to 0, so this operation is well defined. And once it's well defined, all the other properties satisfy. For example, what was that? R plus S, no? R plus S plus I will be an element. The I of each of these element can be taken as a common I. This will give me Rm plus Sm plus Im. So this will go to 0, and R plus Im would have been Rm plus Im, and similarly for S plus Im would have given. So that property is hold. So Rs, let's see what's the product R of S. Let's check the next property. I want to see how I can write this. Just before I write that, let me just check what this expression looks like. Rs plus Ri is I, Si is I, and Ii is I square. Kind of. So this is actually Rs plus I, because I square is less than I, and I has so this is fine. So again the property holds true as R plus I into S plus I. So the I part will go away, and similarly, so all this property holds. So this is also module. Alright, now let's check out another example. Example number D. Continuing further, one can show that if M is an abelian group. I don't know if I mentioned it earlier or not, but in the definition of module, M is required not just to be a group but the abelian group. So let's just take an abelian group. Then there is a default module structure. Default module structure. Can you guess the ring? Yes, the ring R is the ring of integer itself. So how does it work? So if I say n into m, it means you add n times, where addition is the group operation. This is the n times group operation. Alright, similarly, but if this is assuming n is greater than equal to 0. If n equals to 0, then nm equals to 0. Take this as a definition. If n is less than 0, then you just do minus m dot 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 minus m n times. Okay, so this is So these are the 4 main examples. I'll see you in the next video with few more examples and probably few more results. Thank you for listening. Goodbye.